Hi everyone. In the first section 2.3 video, I went through the limit laws and then the general concept and reasoning behind them. In this video, I'm going to show you the calculations needed for section 2.3, and how this will go is it will build up. And so I know when I was younger, especially when I first took math classes, I would say, oh, why is the instructor doing the easiest questions in the notes? I didn't understand. Now I realize that oftentimes if we start with the most difficult or more difficult examples, you lose a larger part of the class at the beginning, and then they don't quite get, where you're going with it because they're confused from the get-go. And I also find that students really need to think through things on their own. So the approach that I take in the notes is I give the concept behind it. I get you started on, the essentials that you need. So it's like I'm adding little tools to your toolbox, and then I want you to use those tools to put things together when you're doing your homework, because you're going to learn a lot more when you're really having to think through things rather than having me try to tell you every single thing and then just have you kind of copy the process. So the reason we have to do that in calculus, and you're going to see this soon, is there are many, many different types of examples, so many that require prerequisite skills that I can't possibly go through everything. So my mindset when I'm teaching calculus is that I have to train you how to think about things, not that I'm going to do a process and then you're going to repeat me. The reason we can't do that is because calculus is just too complicated to have it actually work that way. So in here, I'm going to get you the concept. We're going to go through it. You'll know what you're supposed to do. Where people usually have the challenge is remembering enough algebra to carry themselves through everything. So I'm going to go through a fair bit, but you're absolutely going to want to do your homework and ask questions, meet with me, come to a virtual office hour, post on the discussion boards for things you get lost on. So just really, really important. Okay, another thing that's going to be important is your notation. So I put this over here, often overlooked detail. A lot of times people will drop notation everywhere, and in some classes, beginning math classes, you can kind of get away with it, but in calculus, we have so much notation. A lot of you are going into classes like Calc 4 and Calc 5 and differential equations, and if we don't get you on the notation right now, it's going to make things way more difficult. So think of math like a way of communication. You're using your writing and your notation in a language to communicate a message to myself and to whoever is looking at your work, and really to yourself. So it's important to communicate with the appropriate notation so you understand what you're doing. If you go look at it later, I understand what you're doing, your classmates do, and then, if you have a job that requires calculations or just requires you to communicate, it's important to be concise about that in terms of your notation. Okay, anyway, enough of me talking about those things. Let's get to some examples. So a big tip that I'll give you for when you're starting these algebraic calculations with functions and the limit laws is, if you can, you should simplify first. It just makes things easier for you. This means you need to remember how to factor, how to simplify, properties of exponents, so on and so forth. All right, so let's work through our first example, and quick correction here already. This should be a 0. All right, so we want to calculate the limit as x goes to 0 of x over x cubed minus 2x. All right, notice if you try to plug this 0 in right now, run the limit through right now, you'd get 0 over 0 minus 2 times 0, which is undefined. So that's not helpful. This means that it's going to be really helpful for us to simplify first. So first, let's look for a way to simplify. We write this down here. We have the limit as x goes to 0 of, I have an x up here. All right, looking in the denominator, I can see that I can factor an x out of both pieces. So I have x times x squared minus 2. All right, so here my x's divide out to 1. A quick note on this, a lot of people will say, oh, the x's cancel out. I think it's really important to notice why this cancels out. So this is a side note, but let's look at why that's actually true. It might prevent you from making other mistakes later. So here, if we have the limit as x goes to 0, we can really write this as x over x times 1 over x squared minus 2. Okay, so remember, with fractions, you can multiply. You multiply across the top and across the bottom if you multiply it out. So that would mean this is equal to x times 1, which is just x in the numerator, over x times parentheses x squared minus 2. It's the same thing. So really when I write these little quote unquote cancel, or when I say that, I mean this divides to 1. So since x over x is 1, it allows us to simplify this to the limit as x goes to 0 of 1 over x squared minus 2. All right, so tip, try to do algebra first, see if you can simplify it. All right, and then another thing to notice here is when I went from this first step to the second step, I am not using any limit laws at all. This is simply by algebra. Okay, so I just did some algebra, I simplified, no limit laws. All right, at this point I can see there's no way to simplify this. There isn't any other algebra I can do. So this is when I think, okay, I need to look to the limit laws to see what I can do next. I notice that I have a fraction, which really means I have some function divided by another function. Going back to our limit laws, I notice that by property number 5, I can run limits across division. So I'm not going to expect you to write every single step out like this, and I usually won't either, but I'll do it right now so you can see what's going on. So by property 5, which again, you're not going to have to specify, but I want you to see where I'm getting this from. Okay, I know that this is equivalent to the limit as x goes to 0 of 1 over the limit as x goes to 0 of x squared minus 2. Okay, so now if we're focusing on the numerator, we think, oh, okay, well, I have a limit, I have a constant right here, so what? So just a limit going to a number. So again, I'll go up to my limit laws and see, well, what applies there? We talked about this one. So property number 7 says that if you approach a constant, it's always equal to that constant. So that tells me that the numerator here is just 1, and that's by property number 7, right? We still need to work with the denominator. So looking at the denominator, we see we're taking the limit of two functions that are subtracted. So if we roll back up to those limits, property number 2 says that we can run this limit across subtraction. I probably don't want this line there, sorry about that. Okay, so what this is going to give me is the limit as x goes to 0 of x squared minus the limit as x goes to 0 of 2. So I'm running my limit across subtraction there, and that was, I believe, property number 2. So this is by property 2. All right, let's continue on with this. We are almost done at this point. Coming up here. All right, so we have the 1 on top, already took care of that limit. Okay, now we want the limit as x goes to 0 of x squared. We talked about this property specifically as well. So this is property number 8, and that tells me that really I can just run whatever we're going to, through the x. So I know that this is equal to 0 to the 2, 0 squared, minus, and again we have property 7 right here because we're going to a constant, so minus 2. Right, so in this step, I'm running out of colors here. This was property, I think I said that was 8, I can't remember now. Property 8, maybe I should double check that. Property number 8 discussed above. Okay. And then here, that was just that constant property, which is property number, I might have miswrote that before. I did, okay. Better go back up here. All right, so quick correction, this is actually property number 9. I just misnumbered the ones from above. So this was property number 9, and then the constant property, which we already discussed, was property 7. All right, at this point, I've finished doing all of my limit law work. So now I just need to write what this is equal to. So I'd have 1 over -2, which gives me the final result of -1/2. All right, so like I said with this, I'm showing all the steps, every property. Eventually when you go through this, it'll be more smooth after you practice it more, but I do encourage you to look at the properties when you first start, and that's just so you know that you're not misusing anything or writing things that are untrue. Okay, let's try another one of these. Next example says to calculate the limit as u goes to -2 of the square root of u to the 4th plus 3u plus 6. All right, so looking at this, we see we have a square root. We should notice that there isn't any simplification I can do here. So there's no algebra I can do at the beginning, which means I'm going to turn straight to the limit laws. So now I need to find a limit law that tells me I can run this limit underneath the square root. So scrolling back up again, we see that property number 11 tells us if we have a function underneath a root, we can run the limit underneath that root. So let's go back down here and use property number 11. Okay, so by property 11, we have the limit, the square root of the limit as u goes to -2 of u to the 4th. Right, I'm going to do two things at once here. So notice we have addition in here, and we know that property 1 tells us that we can run the limit over addition. So by properties 11 and property 1, I believe was the addition property, and property 1. Okay, we have u to the 4th plus the limit as u goes to -2 of 3u plus the limit as u goes to -2 of 6. All right, so again, there isn't any algebra that we can do, which means we're going to rely on our properties. So I'm just going to write this as an equal statement. So this is equal to, get our big square root in there. Okay, here, notice that we have u raised to a power again. It's another property. This is equivalent to, this is equivalent to -2 to the 4th, right? And that was from property 9, which we already discussed. So this is from, or by, property 9, right? Plus, okay, here, remember 3 is a constant multiple, so we can pull 3 out in front of the limit, and then just take the limit as u goes to -2. Right, so coming back up to our properties, that was property 3 right here with a constant multiple out in front of a function. You can just take it out of the limit and multiply it back in. So that was property number 3. Okay. Right, next we have plus, and then here we see that we're just going to a constant, so we know that that limit is simply going to be the constant, and again, that was by property 7, which we've seen a few times now. All right, so still haven't finished taking all of our limits. All right, -2 to the 4th is, I believe, and by 32, I mean 16. So -2 to the 4th is a positive 16. All right, oops, I forgot to rewrite the 3u up here. That in there. Okay, so dang it, forgot to write the u up there. We took the 3 out. All right, so here we know that we have the u and the u, they match, so that just goes to a -2. So we have plus 3, just rewriting this part here, times a -2, and again that was by property 8, which we discussed earlier in the notes, so that's property 8. All right, and I'm going to just rewrite the 6 that I have in here. Ooh, okay, so at this point, I ran through all of the limits. I have no more limits in here, which means I can finally finish with my calculations. Right, so this is equal to the square root of 16 minus 3 times -2 is 6, so minus 6 plus 6, which is equal to the root of 16, and that gives us the final answer of 4. All right, so definitely lengthy when you go through and look through all the properties and do every little step, but I think it's best to do it that way until you get really comfortable, and then once you get comfortable, it should go a little bit more quickly, and then your real challenge is going to be remembering a lot of little algebraic processes and steps. Okay, let's try another one. This time we're looking at the limit as x goes to 2 of x squared minus 2x over x minus 2. All right, so on this one, it looks like there is some algebra, there is some simplifying we can do, so let's do that. In the numerator, I can factor out an x to get x times parentheses, x minus 2. In the denominator, I still have x minus 2. Notice that the x minus 2 and the x minus 2 divide out to 1 here, so I'm left with the limit as x goes to 2 of x, and that's really nice, pretty gentle. We can just use one limit law property here, which is pleasant. So by property 7, we can run that 2 through to get 2. Okay, and that is actually by property 8, not property 7. As you can see, I don't have all these memorized. I usually just kind of roll through them. I don't expect you to memorize them either, but I should reference them at least to start. So that was property 8, not property 7. All right, let's try another one. Okay, let's see. For this one, we have the limit as x goes to 4 of x squared plus 3x over x squared minus x minus 12. All right, with this, I'm already seeing there's some factoring I can do, so I'm going to factor and see if we might be able to simplify. All right, and I'm actually going to make this a little simpler, and then we'll do a tougher one after this. So let's make this the limit as x goes to 3 of x squared plus 3x over x squared minus x minus 12. All right, so I haven't taken the limit yet, which means I need to rewrite that limit notation. Okay, in the top, I'm going to factor out, looks like I can factor out an x, so I have x times parentheses x squared plus 3. In the denominator, I see that I have a quadratic, so I'm going to try to factor that into a binomial, so 2 parentheses. All right, so let's see, I know I have an x here, an x here. I need a negative in the middle, so I think if we use minus 4 and plus 3, this should factor. So let's see, pull it out, double check, we have x squared minus 4x plus 3x, that is a negative x, we're good there. 3 times negative 4 is a negative 12, it does factor. All right, here we can see x plus 3 over x plus 3 divides out to 1. So we're left with the limit as x goes to 3 of x over x minus 4 by, I think it's, I can't remember which property 5 maybe, above. I know I can run this over the division. So this is the limit as x goes to 3 of x over the limit as x goes to 3 of x minus 4. Right, now running the limits through, I would have 3 up here. Again, I believe that's property 8, which we've already discussed. I know I can run this across subtraction, so the limit as x goes to 3 of x is 3. And the limit as x goes to 3 of negative 4, which negative 4 is just a constant, is minus 4. So I would get 3 over negative 1, which is equivalent to a negative 3. All right, sorry I had to write some of that sideways. I was running out of space. Key thing to notice here is I kept my limit notation in until I actually ran the limit through. So some people will, I'm not going to leave it like this, but some people will just not write any of these limits in here and then turn it in not showing any limits, and that isn't accurate because if you think about it, you know, this statement with the limit is definitely not the same as this one. So it's really important to hold that limit notation all the way through. All right, so let's try another one. This time we're going to use the same function that we had in example 4. That's the x squared plus 3x over x squared minus x minus 12. But we're going to look to see what happens as the limit, with the limit as x approaches 4. Okay, so we'll start the same way and we'll simplify this. So we know from above that this is equivalent to the limit as x goes to 4 of, let's see, we had x over x minus 4 after we simplified above. Okay, so that was just algebra there. All right, now let's see what happens. So when we did this work above, we simply ran this across the top, ran across the bottom, we were good to go. However, look at this. If we try to run this limit through the bottom, we get something that's not defined, right? So we're gonna have a problem here. Okay, I'll write that out, problem. We can't run the limit. Can't run algebraically. All right, this means that you need to turn to some of your previous knowledge. So in section 2.2, and we really had the concept in 2.1, though we did it with slopes rather than limits, we learned that you can figure out what's going on as x approaches a value by either plugging numbers in to see what happens or by looking at the graph and seeing what happens. I think the numerical method is generally better because sometimes graphs can jump up really quick or you can miss parts of it on your graphing calculator window. So what you're going to do here, if you don't know what's going on, is look at this from the left and from the right. I'll write that out. All right, so using that numerical method, you can pick whatever values you wish. From the left, I chose 3.99 and 3.999. From the right, I chose 4.01 and 4.001. Okay, so since you're just looking at the y values, right, we know limits are approaching y values, I really just need to run this through the function. So I plugged 3.99 into the function I have simplified up here. When I did that, I got negative 399. All right, just a side note, for work here, what I would expect you to do is show your plug-in work at least once, like I did right here, so then I know that you know what you're doing, and from there you can just pop it into your calculator. So I suggest showing it once, because then if you make a calculator work error, I can still see that you know what you're supposed to be doing. Okay, so anyway, when I do this, I see that this is increasing by a lot. If I wanted to test it out further, I could plug in 3.99999, 3.99999, etc., and I would see that this does in fact approach negative infinity. So from this, I see that the limit as x goes to 4 from the left of f of x is negative infinity. All right, coming over here and moving from the right, I get 401, 4001. If I keep going, these would get bigger and bigger and bigger. So I see that, oh no, whoops. I see that the limit as x goes to 4 from the right of f of x, so that's just of my function that I have up here, is infinity. All right, we should remember from section 2.2 that if your y values do not approach the same thing, we say the limit does not exist. So on this one, my final answer is the limit does not exist. All right, so that took more work, but the main concept I wanted to get you to here was that if you go through and you try to do this analytically, but you get that the limit does not exist, then what you're gonna have to do is rely on previous methods, not message. So I always try to do these analytically, algebraically. I encourage that because I do think that there's less room for error, meaning you kind of know exactly what's happening. But if, for whatever reason, the limit doesn't exist after you run through all possible algebra and limit law steps, you may have to resort to another methodology. All right, kind of a lengthy video on this one, but we are on the final example for this video, which is going to be the trickiest one that you'll see in this video, at least. There are going to be tougher ones in the homework though. All right, so for this, we're looking at the limit as h goes to 0 of 3 plus h to the negative 1 minus 3 to the negative 1 over h. All right, from the beginning, I know that I can't just run the limit through, and that's because I have 0 in the denominator, so that's definitely not going to be an option. All right, the next thing that I want you to take note of is when you have negative exponents, oftentimes it's better to not have the negative exponents, and that's because it allows you to do more algebraically. So since I can't run through limits right now, since I have no limit laws that say I can run the limit underneath a negative exponent, what I'm going to have to do is rewrite this so I can actually work with it. So this is the same as the limit as h goes to 0 of 1 over 3 plus h. All right, so properties of exponents, if it's raised to the negative, it drops down into the denominator. Technically, this is parentheses to the first power, but I don't really need to write that because this is equivalent. All right, minus, so I'm just holding this minus sign. 3 to the negative 1 is the same as 1/3. All right, I have all of that over h. Okay, so from here, I can't run the limit yet because I still have something undefined in the denominator. So what I have to take note of is it is the denominator that's causing me the issue. I need to somehow figure out how I can undo, how I can get rid of the denominator to allow me to run this limit. So essentially my goal is to cancel or to divide this h right here out. Okay, in my numerator, if my fractions are smashed together, my fractions are separated like this, what I need to do is try to push them together by getting a common denominator, because it allows me to flip things around and work with them a little bit more. So this is a very large prereq type question, but we need to find the common denominator between 1 over 3 plus h minus 1/3. So we need some side work here, all algebra. Okay, and what I'm going to do is find the common denominator. Okay, so I have 1 over 3 plus h, 1/3. Okay, good common denominator for these two is going to be found by multiplying the two denominators together. So we need to get this to 1 over 3 times 3 plus h. Okay, sorry, something over 3 times 3 plus h. And then gotta get the numerator there, but I know I want my denominator to be 3 times 3 plus h. All right, so looking at this, to get from 3 plus h to 3 times 3 plus h, I'm going to have to multiply by 3. You always have to do the same thing to the top as you do the bottom. That's what allows you to hold equivalence. So here, notice that 3 over 3 is 1. So it's just like multiplying this fraction by 1. You're essentially just making it look different so you can work with it. All right, so this numerator is 3. All right, down to our second equation, right? To get from 3 to 3 plus 3 times h, I need to multiply, to get from 3 to 3 plus h, I need to multiply by 3 plus h. Right, have to do the same thing to the top, so then it's just like multiplying by 1, which means you're not changing your expression at all. Right, so here I get a 3 plus h. All right, now I can go through and substitute that into my original equation. And I don't like that there. It's okay. All right, this is equivalent to the limit as h goes to 0 of 3 over 3 times 3 plus h minus 3 plus h over 3 times 3 plus h. All of that is divided by h. Okay, since we have a common denominator, I can now combine these two fractions together. So this is equivalent to limit as h goes to 0 of 3 minus 3 plus h over 3 times 3 plus h all over h. Okay, I'm going to do a couple of things in this next step. I'm going to simplify the numerator. So as h goes to 0 of 3 minus 3, there is 0. So I just get h in the numerator, and then I have that over 3 times 3 plus h. Right, I also want you to notice that in the denominator here, h is the same thing as h over 1. Hopefully you remember from previous algebra classes that when you divide a fraction by another fraction, you can just flip the denominator and multiply. So this is the same as saying times 1 over h. So I flipped and multiplied. All right, now this is exactly where we want to be. So remember, our goal was to get rid of this h so we could run our limit through. Well, if you look at what we have at this point, we have an h in the numerator, h in the denominator. H divided by h is 1, so we are able to divide that out to 1, which leaves us with the limit as h goes to 0 of 1 over 3 times 3 plus h. All right, now thinking about our limit, we see we can definitely run that through the top. It's just a constant, so the limit of a constant is always itself. We get 1 there. All right, coming through the bottom, I know I can run this across multiplication, and I have a constant I can factor out. So I get 3 times, 3 is a constant, so 3 plus, now I have h going to 0, so I know this piece goes to 0. Okay, this allows me to finish my calculations and get 1 over 3 times 3, which is just 9. All right, and looking back through this, wanted to see if we'd think about this, but there is a really small mistake, and this is something that people do all the time. So we should have noticed that up here, when I combine these two, I just wrote the minus, but I forgot something, and that is the parentheses. So remember, when you're going through these and you find a common denominator, you always have to hold this sign through everything. So that would mean that this has to be negative, this is negative, this is negative, and my final answer is negative. So have to be really careful with that part of it. Okay, so I know that this video was pretty lengthy and I went through a little bit of algebra. You're going to find that when you go through this on your own, like I said, a lot of times you're going to have to remember a lot of algebra. So sometimes there'll be things like factoring when you have, summation of perfect squares or perfect cubes, etc. You might have to look a few things up. You might have to ask questions. Try not to get frustrated. And then sometimes, just going to tell you how it works, you'll go through these limits and be like, oh shoot, I'm stuck, and realize that you made a mistake and you have to go back through. So if you remember the trig proofs from pre-calc 2, it'll be sort of like that in the sense that you have to sort of figure out what to do and when, and the process will differ a little bit every time, but as you practice more, you'll be able to look at them and get a better idea of where you're probably going to have to go with it. All right, so really important to do your homework on this one. Make sure you do it, and I also recommend doing the practice handout for this week as well. Okay, thank you.